Imagine standing on the edge of a construction site.
Mm-hmm.
And not just a building, but a massive sprawling industrial complex.
Right.
Cranes dotting the skyline, thousands of workers, the low hum of heavy machinery just kind of shaking the ground.
It's a completely different scale.
Exactly. Now take that image and multiply it by dozens, just spread across an entire coastline. Because, when we usually talk about infrastructure, we think in terms of like a single bridge or maybe a high-speed rail line.
Sure.
But right now, we are witnessing an energy infrastructure build-out on a scale that you and I, that the world hasn't really seen since the mid-20th century.
Yeah, it really is a mobilized, national-level industrial effort. And it is fundamentally redrawing the global energy map literally week by week.
Yeah.
We are looking at a system operating with a level of capital and just sheer engineering velocity that, honestly, it challenges all our standard assumptions about heavy infrastructure.
It really does,
Right.
Which is why we are taking a deep dive into the raw data today. We want to really understand the mechanics behind this build-out for you.
Right.
So we're bringing you a factual, up-to-the-minute news briefing and status update on China's nuclear power construction. And this is specifically for the week ending June 28th, 2026.
Exactly.
And just to be clear on where we're getting this, we're drawing on a stack of industry updates. Specifically, we've got reporting from World Nuclear News, NucNet, operational data from the China General Nuclear Power Group.
Which we'll just call CGN for short.
Right, CGN.
Yeah.
And also official capacity targets broadcast by the state network, CCTV. So, okay, let's unpack that.
Sounds good. Let's start with the macro picture based on this late June 2026 data. So right now, China operates 62 commercial nuclear units.
Wow, 62.
Yeah, 62. And that gives them a combined gross capacity exceeding 60 gigawatts electric, or GWE, as it's called.
Okay, let's contextualize 60 gigawatts electric for a second, because that's a massive number.
It is.
Because, 1 gigawatt is roughly enough to power about 750,000 average homes.
Right.
So 60 GWE, that represents the base load, always on power, for upwards of 45 million households.
It's staggering when you put it like that. And that puts them at number 2 in the world, trailing only the United States, which operates 94 commercial units.
Got it.
But the metric where China really separates itself from the rest of the global market is the construction pipeline.
Right, the stuff they're building right now.
Exactly. They currently have 39 units under active construction. That totals about 37.3 gigawatts of new capacity.
That's just wild.
And they have actually held the #1 spot globally for reactors under construction for 19 consecutive years now.
19 years, wow.
Yeah. And the stated policy targets reflect that momentum too. So the 15th five-year plan, which was approved back in March 2026, it codifies a target of 110 GWE by 2030.
Okay.
And then the China Nuclear Energy Association projects hitting 150 GWE by 2035.
Wait, I have to push back on that 150 GWE figure.
Okay, go ahead.
Because adding essentially 150 modern reactors to the grid in under a decade, that requires a just staggering amount of capital.
It does.
And we know the broader Chinese economy is currently navigating some pretty significant headwinds, right? There's a well-documented real estate slump, consumer spending challenges, local government debt issues.
Yeah, all true.
So financing a pipeline of this magnitude in the current economic climate, it just seems like an impossible math problem. How are they structurally affording to build the equivalent of a medium-sized country's entire energy grid from scratch every few years?
Well, if we connect this to the bigger picture, the financing model is actually somewhat insulated from those specific consumer and real estate headwinds.
Oh, really? How so?
Because it relies heavily on state-backed policy banks. And these banks view energy security as a non-negotiable strategic imperative. It's not just about standard market returns.
Okay. That makes sense.
But beyond the money, the real answer to how they build so much so quickly comes down to industrial standardization.
Right.
In the West, nuclear power plants have historically been treated as bespoke megaprojects. Every site has custom engineering, unique supply chain bottlenecks, specialized labor requirements.
Like every single plant is a one-off custom build.
Exactly. But China is shifting nuclear from a construction paradigm to a manufacturing paradigm.
So they are essentially applying Henry Ford's assembly line to nuclear physics.
That is a great way to put it.
Like, instead of building a reactor from scratch on site, They have specialized factories just churning out pressure vessels and steam generators in a continuous loop.
Yes, and then those parts are just shipped and assembled on location. That approach allows them to run multiple parallel construction tracks across different provinces without, starving their specialized manufacturing base of resources.
Wow.
And we really see the result of that factory-like cadence in the immediate commissioning targets. For example, the state broadcaster, CCTV, recently announced a target to bring 7 reactors into commercial operation in calendar year 2026 alone.
Wait, 7 in a single year?
Yep, 7.
That requires an incredibly tight sequence of regulatory and physical milestones.
Mm-hmm.
And I know we are actually seeing that sequence play out in real time this week down in Guangdong province, right, at Taipingling Unit 2.
Yes, exactly.
And this is 11,116 megawatt Hualong One reactor, which is their flagship indigenous design.
Right, the Hualong One. And the timeline for Taipingling Unit 2 over the last 90 days really illustrates the speed of this pipeline.
Let's hear it.
So they received their 40-year operating license from the National Nuclear Safety Administration on April 30th.
Okay.
Then, just 3 days later, on May 3rd, they completed the first fuel loading. They inserted 177 fuel assemblies into the core.
Wow, 3 days.
Yeah. And then on June 25th, at exactly 00.22, the reactor achieved first criticality.
Okay, let's pause there for a second. For those of us who, don't operate nuclear plants on the weekends, what exactly is first criticality? Because I often hear it explained as turning the key in the ignition of a car.
Yeah, that's a common analogy.
But that feels a bit, I don't know, passive for what is actually happening at the atomic level. It's got to be far more dynamic than that.
It is.
So a better way I like to visualize first criticality is to imagine sitting in a heavy manual transmission truck on a really steep hill.
Okay, I like where this is going.
You know that feeling where you have to find the exact bite point between the clutch and the gas pedal to hold the truck perfectly still?
Right, yeah.
You are balancing the forces. So the system is self-sustaining, it's not stalling out, rolling backward, and it's not surging forward. In a reactor, you are balancing the neutron population.
That is a phenomenal way to describe the physics, really. Because when a reactor reaches criticality, the operators have basically configured the control rods and the coolant so that each fission event releases exactly enough neutrons to trigger one additional fission event.
Ah, so it's a perfectly sustained equilibrium.
Exactly. And the moment you achieve that balance, the facility basically transforms from a highly complex assembly of steel and concrete into an active, living nuclear system.
Wow. It's like the ultimate threshold before they scale up the heat, produce steam, spin the turbines, and actually synchronize the plant with the regional electricity grid.
Precisely. And CGN expects Taipingling Unit 2 to reach that final stage of full commercial operation later this year, which will check off one of those 7 targeted commissionings for CCTV.
Amazing. But, the journey to that critical bite point starts much earlier. And I want to look at what happens in the months before the uranium even arrives on site.
Right, the pre-commissioning phase.
Yeah, because our sources highlighted a crucial microscopic milestone at a totally different facility this week. Down on Hainan Island, Changjiang Unit 4 commenced what they call nuclear loop flushing on June 22nd.
Yes, loop flushing is such a fascinating quality assurance gateway.
It sounds intense.
It really is. A modern reactor relies on an incredibly complex network of primary pipelines. You've got the reactor coolant system, the residual heat removal system, the safety injection network.
Just miles of piping.
Exactly. And during a typical 60-month construction cycle, despite maintaining immense cleanroom protocols, microscopic debris inevitably enters these systems.
Oh, sure. Dust, welding slag, maybe tiny metal shavings from a saw.
Exactly.
So my mind immediately goes to, power washing a multi-billion-dollar plumbing system. But the stakes are existential here, aren't they?
They absolutely are.
We aren't just worried about a clogged pipe under the kitchen sink. When a reactor is actually running, the water inside those loops is under roughly 150 atmospheres of pressure, and it's heated to over 300 degrees Celsius.
Right.
In that environment, a tiny metal shaving isn't just debris. It behaves like a high-velocity projectile, which threatens the integrity of the coolant pumps.
That's true, but the threat actually goes even deeper into atomic physics.
Really? How so?
Yeah. If an impurity, say a microscopic flake of cobalt from a steel alloy, floats through the reactor core while it's operating, it can actually absorb neutrons.
Oh, wow.
This process is called neutron activation. So that tiny, harmless flake of metal suddenly becomes a highly radioactive isotope.
Oh, that's not good.
No, because then it circulates and plates out on pipes and valves outside the core, and that makes future maintenance a severe radiation hazard for the workers.
Right. So they use this high-velocity fluid to flush the entire system before the nuclear fuel is ever introduced.
Exactly. They have to verify the flow capacity and prove absolute leak tightness. Because as you can imagine, once the system goes active, you cannot simply send a plumber in with a wrench to tighten a loose valve.
Definitely not. And, the regional context of the Changjiang site adds another layer to this whole thing.
How so?
Well, Henan province has a population of around 10 million people. And because it's an island, importing massive quantities of coal or liquefied natural gas is logistically inefficient.
Right. The shipping costs alone would be huge.
Exactly. Plus, they lack the sprawling landmass required for gigawatt-scale solar farms. So their localized energy policies have explicitly dictated that nuclear power will become the primary source of electricity for the entire provincial economy.
That's a huge commitment.
It is. Changjiang isn't just an addition to a national grid. It is the fundamental heartbeat of Hainan's future infrastructure. And both Phase 2 units there, Units 3 and 4, are scheduled for operation in early 2027.
It really puts the importance of that loop flushing into perspective.
It does. Okay, so we've looked at the microscopic level with loop flushing and the atomic level with first criticality. Now let's kind of zoom out to the macro civil engineering required to even house these massive systems.
Let's do it.
Because at the Ningde nuclear plant in Fujian province, Unit 5 just hit a major construction milestone. They hoisted the containment dome into place.
Oh, the dome lift. This is always impressive.
Right. According to Nuclear Engineering International, this steel dome weighs 270 tons and measures 45 meters across. And they lifted it and set it perfectly in place in 2 hours and 45 minutes.
Yeah, for sense of scale, for you listening, a 270-ton payload is roughly equivalent to lifting a fully loaded Boeing 777 commercial airliner.
That is just insane to think about.
And the engineering tolerances are incredibly unforgiving. I mean, you are maneuvering this massive weight outdoors. So you're subject to coastal wind shear, atmospheric pressure changes.
And even just the heat from the sun, right?
Right. The thermal expansion of the steel itself as it sits in the sun. The crane operators basically have to thread a needle in the sky, aligning these massive steel segments with millimeter precision.
It's incredible. But beyond the sheer logistical spectacle of, lifting an airplane-sized steel lid onto a building, this specific event actually signals a very hard pivot in the life cycle of the project.
It does. The containment dome lift demarcates the boundary between civil construction and mechanical installation.
Okay, break that down for us.
Well, for the first 2 years of a project like Ningde Unit 5, the site is essentially a conventional heavy construction zone. You're pouring thousands of tons of concrete, weaving dense matrices of rebar, building the structural shell.
Messy stuff.
Exactly. But the moment that dome is welded into place and the building is sealed off from the elements, the environment completely changes.
It becomes an industrial clean room.
Yes.
Like you finish the heavy, dirty framing of the house so you can safely bring in the incredibly sensitive, delicate, and frankly expensive electronics without worrying about rain, humidity, or that coastal salt air compromising the components.
Precisely. And Ningde Unit 5 poured its first concrete back in July 2024. Now, 2 years later, the dome is sealed, and they are pivoting to that internal equipment installation.
Fast work.
Very. Commercial operation is slated for 2029. But, the consistency of these construction timelines brings up arguably the most vital takeaway from this week's data.
Which is?
We need to look closely at what is actually sitting under these domes, because China is not just photocopying a single blueprint 39 times.
Oh, absolutely not. The diversity of the technology pipeline is staggering. I mean, if we run through the active builds from the sources, they are constructing indigenous Hualong One reactors at Taipingling and Ningde, like we just talked about. But they are also building CAP-1000s, which are advanced derivatives of the American AP-1000 design. And then up at Sudapu, they are constructing Russian-supplied VVER-1200 reactors.
Yeah, and what's fascinating here is that the portfolio expands well beyond traditional pressurized water reactors.
Right.
In Xiapu, they are advancing the CFR-600. And back at the Changjiang site on Hainan, right alongside the massive gigawatt units we discussed earlier, they are building the Linglong One.
Also known as the ACP-100.
Exactly.
The jargon in nuclear engineering can be an incredibly dense barrier to entry. So let's decode some of these systems for everyone, starting with the Linglong one.
Okay, good idea.
This is an SMR, which stands for Small Modular Reactor. So instead of a massive facility requiring a sprawling coastal footprint, an SMR contains the steam generators, the coolant pumps, and the reactor core, all within a single, much smaller pressure vessel.
Yeah, it's incredibly compact.
Right. And it's designed to be fully manufactured in a factory, shipped on a standard truck or rail car, and then just plugged into a decentralized grid or an industrial park. It actually passed the IAEA safety review back in 2016, and it could very well become the world's first commercial land-based SMR to enter service.
Yeah, and the Linglong one serves a very specific market need for smaller, flexible power generation. But the other one I mentioned, the CFR 600 in Jiapu, that serves an entirely different strategic purpose.
Right.
That unit is a generation of the fifth sodium-cooled fast reactor.
Okay, let's unpack the sodium-cooled fast reactor concept because the physics here are just fascinating.
They really are.
Traditional reactors use water for two main reasons. First, to cool the core, and second, to act as a moderator to slow down the neutrons.
Right, because slowing down the neutrons makes it easier for them to collide with uranium-235 and sustain the chain reaction.
Exactly. But a fast reactor removes the water entirely. They want the neutrons moving at maximum velocity. But obviously, you still have to remove the immense heat. So instead of water, they pump liquid sodium metal through the core.
Yeah, and using liquid metal allows the reactor to operate at much higher temperatures without requiring the massive pressure vessels that water-cooled systems need.
Because liquid sodium doesn't boil and turn into steam at those temperatures, right?
Exactly. But more importantly, those high-speed neutrons can fundamentally change the nuclear fuel cycle.
This is the crazy part.
It is. Fast reactors can actually consume the long-lived radioactive isotopes that traditional reactors leave behind as nuclear waste. They extract significantly more energy from the same amount of mined uranium, basically closing the loop on fuel efficiency.
So they are literally turning legacy nuclear waste into an active fuel source.
They are.
That is just brilliant. And, the innovation doesn't even stop there. We also have to highlight the Shidawon facility in Shandong province because they are already operating the HCRPM,
Yeah.
which is a high-temperature gas-cooled pebble bed module.
The pebble bed design radically alters how we think about fueling a reactor.
Yeah, a pebble bed almost sounds like, I don't know, a landscaping feature.
It does, a little bit.
But the engineering is brilliant. In a traditional reactor, the uranium is stacked into long, rigid metal rods. And to refuel it, you have to shut the entire plant down, open the high-pressure vessel, and carefully extract these rods.
Oh, huge process.
Right. But in a pebble bed system, the uranium is encased inside these billiard ball-sized spheres of graphite. So you basically have a massive hopper of these radioactive graphite balls. The operators just drop fresh pebbles in the top and pull spent pebbles out the bottom, continuously refueling the plant while it runs at full power.
It's so clever, and the inherent safety of those graphite pebbles is really the true breakthrough.
How so?
Well, graphite can withstand temperatures far beyond the melting point of the uranium fuel inside it. So even if the plant somehow loses all power and all coolant mechanisms fail simultaneously.
The worst-case scenario.
Exactly. Even then, the physical properties of the graphite ensure the core simply radiates heat away without ever melting down. It is what we call a walk-away safe design.
Walk-away safe. That is incredible. And what is so striking when you look at all of this together, the Hualong Ones, the SMRs, the fast reactors, the pebble beds, is that China has essentially transformed its power grid into a live commercial-scale testing ground for the entire spectrum of global nuclear technology.
They really have. They are essentially running a massive empirical experiment.
Yeah.
If small modular reactors prove to be the future of decentralized grids, well, they will already have a working commercial model. If fast reactors are the key to long-term fuel sustainability, they already have the supply chain active.
Right.
They aren't waiting for the international community to settle on a single standard. They're just building all of them at scale to determine firsthand what is most efficient.
Which really brings into focus the true takeaway from this week's data. Because whether we are analyzing the baseline of 62 operational units or the 39 units under construction, or even the highly specific milestones like Taipingling achieving criticality and Ningde hoisting a 270-ton dome, the sheer volume is historic.
Absolutely.
But the execution speed is what matters most.
Hmm.
We are seeing these massive, complex infrastructure projects like the units at Beilong and Changjiang adhering to incredibly strict 56 to 60-month timelines.
Yeah, that consistency is key.
They are consistently moving from the first concrete pour to full commercial power generation in under 5 years.
The pipeline is active, it's highly capitalized, and it's incredibly technologically diverse. But as with all major industrial and geopolitical developments, it is essential to view these reports objectively. So before we wrap up, we want to remind you that this report has been prepared for informational purposes only. It does not constitute investment advice, a solicitation, or an offer to buy or sell any securities or financial instruments. The information is compiled from publicly available sources believed to be reliable, but no representation or warranty is made as to its accuracy, completeness, or timeliness. Nuclear project timelines and capacities are subject to change and should be verified against official regulatory filings.
Thanks for that.
Yeah.
And to close out this deep dive today, I want to leave you with one final thought to sort of mull over on your own.
Okay.
We have spent the last 20 minutes or so detailing how China is proving they can build advanced, diverse nuclear reactors reliably, safely, and in exactly 5 years using a highly standardized manufacturing approach.
Right.
Well, consider the massive global demand for clean baseload energy, especially in developing nations that lack their own domestic nuclear engineering sectors.
It's a huge market.
So what happened to the global energy map when China starts actively exporting that turnkey construction capability, literally delivering a fully operational walk-away safe power plant in just 5 years to the rest of the world over the next decade?
That's the big question.
It is a shift in the geopolitical energy equation that extends far beyond their own coastline. Thanks for joining us as we unpack the data today and keep questioning the mechanics behind the headlines.